Picture this. Beneath the border of France and Switzerland, inside a tunnel 17 miles long, scientists just detected something that shouldn't exist. Something that violates every law of physics we've spent centuries building. Something that suggests our entire reality might be a temporary glitch in a far stranger cosmic machine. And what they found isn't just academically interesting. It's potentially the most terrifying and exhilarating discovery in human history. I'm talking about anomalies in particle decay that suggest the fabric of spacetime itself has microscopic cracks running through it. Cracks that are growing. And through these cracks, scientists at CERN have glimpsed something that makes absolutely no sense, according to our current understanding of the universe. What if I told you that reality as you experience it right now, this moment, reading these words, might be fundamentally unstable? That the universe you inhabit could be balancing on a knife's edge, and what CERN just discovered might be the first sign that we're about to fall off. Before you think this is science fiction, let me be clear. This isn't speculation from the fringes. This is coming from the Large Hadron Collider, the most sophisticated scientific instrument ever built, operated by thousands of the world's leading physicists. And what they're seeing in their data is keeping some of them awake at night. Now, before I blow your mind completely, do me a favor. Hit that like button and subscribe to the channel, because what I'm about to explain will fundamentally change how you see reality. And drop a comment below telling me what country you're watching from and what time it is where you are. I'm genuinely curious how far this message spreads around our fragile little reality bubble. Let's start with what CERN actually does, because most people have this completely wrong. The Large Hadron Collider isn't just smashing particles together for fun. It's recreating conditions that haven't existed in our universe since microseconds after the Big Bang. They're essentially building tiny, controlled Big Bangs over and over, billions of times, and watching what emerges from that primordial chaos. Think of it like this. Imagine you wanted to understand how a car works, but you've never seen inside one. You could try to carefully disassemble it piece by piece. Or you could crash two cars together at immense speed and watch what parts fly out and how they interact. That's essentially what particle physicists do, except instead of cars, they're crashing protons together at 99.9999991% the speed of light. When these protons collide, they release energy so intense it converts back into matter, following Einstein's famous equation, E equals mc. In these collisions, particles spring into existence that haven't been seen in our universe for 13.8 billion years. Particles with exotic names like W bosons, Z bosons, top quarks, and the famous Higgs boson discovered in 2012. But here's where things get strange. In 2023 and early 2024, CERN scientists started noticing something odd in their collision data. Certain particle decay patterns were showing up that shouldn't be there. Tiny statistical anomalies that most people would dismiss as experimental error or random noise. Dr. Gianfrancesco Giudici, head of CERN's theory department, first spotted these irregularities in what's called B-meson decay. Now, B-mesons are particles that contain a bottom quark, and they decay in predictable ways following what's called the standard model of particle physics. This model has been tested millions of times, and it works with extraordinary precision. It's probably the most successful scientific theory ever created. But the B-mesons weren't behaving. They were decaying into combinations of particles at rates that differed from predictions by about 3 standard deviations. That might not sound like much, but in particle physics, when you're dealing with billions of collisions, 3 standard deviations means something genuinely strange is happening. Then they noticed the same anomalies appearing in muon behavior. Muons are like heavy electrons, and at Fermilab in the United States, physicists had already been scratching their heads over muons that were wobbling in magnetic fields slightly differently than predicted. The CERN data was showing similar weirdness. Dr. Mitesh Patel from Imperial College London, working with the LHCb experiment at CERN, published findings in late 2023 that showed these anomalies weren't random. They had a pattern. And that pattern pointed to something extraordinary, the possibility that spacetime itself has defects in it. Now here's what will blow your mind. The leading theory to explain these anomalies is that our universe exists in what's called a false vacuum state. To understand this, imagine reality as a ball sitting in a valley between two mountains. Our valley, our version of physics, feels stable, but it might not be the lowest valley possible. There might be a deeper valley on the other side of the mountain, a lower energy state where the laws of physics are completely different. And if that's true, our entire universe is metastable. It's like a supersaturated solution in chemistry, waiting for one tiny disturbance to trigger a cascade that transforms everything. The particles CERN is seeing, the weird decay patterns and anomalous behaviors, might be quantum fluctuations that are literally testing the stability of our vacuum state. Dr. Joseph Leiken, a theoretical physicist at Fermilab who collaborates with CERN, put it bluntly in a 2024 interview. The universe wants to be in a different state. Our physics, our matter, our very existence might be cosmically temporary. And we might be seeing the first signs that the transition is beginning. Let me pause here, because I need you to understand the implications. If our vacuum state is false, if reality is sitting in the wrong valley, then it's possible, maybe even inevitable, that someday, somewhere in the universe, a quantum fluctuation will occur that tips the universe into the true vacuum state. When that happens, a bubble of different physics will form and expand outward at the speed of light, rewriting the laws of nature as it goes. Everything in its path would be destroyed and reorganized according to new physical laws. Atoms might not be able to form. The forces might be completely different. And there would be no warning. One moment you're sitting here watching this video, and the next moment, before any signal could reach your brain, the bubble would hit, and you, me, Earth, the solar system, everything would cease to exist as we know it. Sleep well tonight. But before you panic, let me explain what CERN actually found and why it's both more subtle and more fascinating than any simple doomsday scenario. Because the real story involves something called quantum foam, the holographic principle, and the possibility that our universe might be leaking. You're still here. Good. That means you're ready to go deeper. Let me build your understanding from the ground up, because what comes next is going to challenge everything you think you know about reality. Let's start with something that sounds simple. What is reality made of? You probably learned in school that everything is made of atoms. Atoms are made of protons, neutrons, and electrons, and we're done. But that's not where the story ends. It's barely where it begins. Protons and neutrons are made of smaller particles called quarks, held together by particles called gluons. Electrons are fundamental, meaning they're not made of anything smaller as far as we know. But here's the weird part. When you try to measure how much space these particles actually take up, you run into a bizarre problem. They might not take up any space at all. They might be mathematical points, infinitely small, with literally zero volume. Think about that. You, your body, everything you can touch is made of particles that might have no actual size. It's like saying a perfectly sharp pencil point, but sharper, infinitesimally sharp, contains all the properties of matter. Your entire existence might be built from geometric points that don't technically occupy space. But it gets stranger. These particles aren't really particles most of the time. They're waves. Or rather, they're something that we can only describe mathematically as being both particle and wave, neither and both, until we measure them. This isn't poetic language. This is literal. An electron exists as a spread-out wave of probability until you observe it, at which point collapses into a definite position. The famous double-slit experiment proves this beyond any doubt. Fire electrons one at a time through two slits, and they create an interference pattern on the screen behind them. exactly like waves do. Each individual electron somehow goes through both slits simultaneously, interferes with itself, and creates a pattern that's impossible if it's just a particle following a single path. But the moment you measure which slit the electron goes through, the interference pattern disappears. The act of observation changes reality. Dr. Anton Zeilinger won the Nobel Prize in Physics in 2022 for experiments proving that this isn't just about our knowledge. It's not that the particle was always in one place, and we just didn't know it. Before measurement, the particle genuinely doesn't have a definite position. Reality is fundamentally probabilistic, not deterministic. Now, here's where we connect this to spacetime itself. Einstein showed us that space and time aren't separate things. They're woven together into a four-dimensional fabric called spacetime. And matter and energy curve this fabric. That curvature is what we experience as gravity. A massive object like Earth creates a depression in spacetime, and objects roll toward it, the way a marble rolls toward a bowling ball on a stretched rubber sheet. This has been confirmed thousands of times. GPS satellites have to account for the fact that time runs slightly faster orbit than it does on Earth's surface because they're in a weaker gravitational field, which means spacetime is less curved. The corrections are tiny, about 38 microseconds per day, but without them, GPS would drift by several miles in just a few hours. But Einstein's picture of smooth, continuous spacetime breaks down when you zoom in far enough. At scales around 10 to the negative 35 meters, something called the Planck length, spacetime itself becomes quantum. It stops being a smooth fabric and becomes a seething foam of quantum fluctuations. Virtual particles pop in and out of existence. The geometry itself becomes probabilistic, fuzzy, uncertain. This is quantum foam, predicted by physicist John Wheeler in the 1950s. At the smallest scales, spacetime isn't a stage where events happen. It's an active participant, fluctuating wildly, and these fluctuations might be what we call the zero-point energy of the vacuum. Here's the mind-bending part. This quantum foam means that empty space isn't empty. The vacuum is full of energy, and that energy has real measurable effects. One of the most famous is the Casimir effect, discovered in 1948. Put two metal plates very close together in a vacuum, and quantum fluctuations outside the plates push harder than fluctuations between the plates, because the gap is so small that only certain wavelengths fit between them. The plates attract each other from literally nothing. This vacuum energy is real. And according to quantum field theory, when you calculate how much of it there should be, you get an absurdly large number. So large that if it was accurate, the universe would have collapsed into a black hole instantly at the moment of the Big Bang. Obviously, that didn't happen, which means something is canceling out most of the vacuum energy. But we have no idea what or why. This is called the cosmological constant problem, and it's one of the deepest mysteries in physics. The vacuum energy we observe, measured through the expansion rate of the universe, is about 120 orders of magnitude smaller than quantum field theory predicts. That's not a small error. That's like predicting someone weighs 10 to the 120 kilograms, and they actually weigh 1 kilogram. Something is very, very wrong with our understanding. And this is where CERN's discovery becomes terrifying. What if that cancellation isn't perfect? What if the vacuum energy in our universe is balanced, but barely, like a coin standing on its edge? What if there are places, microscopic cracks in spacetime, where the balance fails and the true vacuum energy starts to leak through? That's what the anomalies at CERN might be showing. The weird particle decays, the unexpected behaviors, they could be particles interacting with quantum foam in ways that reveal structural defects in spacetime itself. Dr. Lisa Randall from Harvard, one of the leading theoretical physicists working on extra dimensions and the geometry of spacetime, proposed in her work that our universe might be a three-dimensional membrane, a brain, floating in a higher dimensional space. And if that brain has wrinkles or tears, even microscopic ones, the physics in those regions would be different. Particles passing through those regions would behave abnormally. The CERN data fits this picture disturbingly well. It's not that every particle behaves strangely. It's that occasionally, seemingly randomly, particles do things they shouldn't, as if they're briefly interacting with a defect in the underlying structure of reality. Think of it like this. Imagine you're driving on a perfectly smooth highway. Most of the time, your ride is smooth and predictable, but occasionally, you hit a pothole. Not a big one, just a small divot that gives your car a tiny jolt. Most drivers wouldn't even notice, especially at highway speeds. But if you had incredibly sensitive instruments measuring your car's vibrations, you'd detect those potholes clearly in your data. That's what CERN is doing. They're driving particles at cosmic highway speeds and detecting the tiny jolts that suggest spacetime has potholes, cracks, defects, places where the geometry isn't quite right. Now here's where I need you to stay with me, because the next part sounds like science fiction, but it's where cutting-edge physics is actually heading. What if those cracks are growing? One of the properties of vacuum decay, if our universe is in a false vacuum, is that it can be triggered. High-energy events, like the collisions at CERN, or even more energetic cosmic ray collisions, could theoretically nucleate a bubble of true vacuum. Once started, that bubble would expand at light speed, converting everything it touches. We don't think CERN is powerful enough to trigger this. The universe has been bombarding itself with far more energetic cosmic rays for billions of years without ending. But what if CERN isn't triggering vacuum decay? What if it's detecting early signs that vacuum decay is already happening somewhere in the universe, and the effects are propagating through quantum entanglement or some other mechanism we don't understand? This might sound crazy, but remember, quantum entanglement is real. Einstein called it spooky action at a distance, and he hated it, but it's been proven over and over. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. Not through any signal traveling between them, but through a connection that transcends space itself. What if space-time defects create entanglement patterns that spread their influence non-locally? What if reality can crack in one location, and the instability can appear elsewhere without propagating through the space between? I know that sounds insane, but Dr. Leonard Susskind at Stanford, one of the founders of string theory, has been working on exactly these kinds of questions. His work on the holographic principle suggests that the information content of any region of space is actually encoded on its boundary, like a hologram. The three-dimensional reality we experience might be a projection from information stored on a two-dimensional surface. If that's true, then defects in the holographic encoding could manifest as anomalies anywhere in the projected volume. A crack in the underlying information structure could show up as particle physics weirdness at CERN, and the crack itself might not even be located in our three-dimensional space. It might be in the higher dimensional boundary. Are you starting to see why physicists are both excited and nervous? The CERN anomalies are like seeing the first tiny cracks in a windshield. You don't know if they'll spread, or how fast, or what will happen if they do. But you know something fundamental just became unstable. Before we go further, I need you to engage with this. Drop a comment telling me if you've ever had a moment where reality felt wrong, where things seemed glitchy or off. I'm serious. Given what we're discussing, I'm genuinely curious if human consciousness somehow detects these instabilities. Hit like if this is blowing your mind so far, because we're just getting started. Let me take you inside CERN's discovery process, because understanding exactly what they found and how they found it will make everything that follows even more mind-blowing. The Large Hadron Collider is a ring, a circular tunnel 27 kilometers around, buried about 100 meters underground. Inside this tunnel, two beams of protons travel in opposite directions at 99.999999991% the speed of light. When physicists want to see what happens, they cross the beams, causing protons from each beam to collide head-on. Each collision releases about 13 trillion electron volts of energy, concentrated in a space smaller than an atom. For context, that's about 13,000 times the mass energy of a proton, all released in a volume billions of times smaller than a grain of sand. The energy density is so extreme that it's similar to conditions 1/trillionth of a second after the Big Bang. In these conditions, the energy converts to matter. But not just any matter. The universe doesn't care what particles existed before. It only cares about energy and the rules for converting that energy to mass. So in every collision, a spray of particles emerges, following the probabilistic rules of quantum field theory. Most of these particles are mundane, things we've seen millions of times. But occasionally, something rare appears. A Higgs boson, a top quark, or something we've never seen before. To detect these particles, CERN built massive detectors around the collision points. The biggest is called Atlas, which weighs 7,000 tons and has 100 million sensors. These sensors track every particle that emerges from a collision, measuring their energy, momentum, and trajectory with absurd precision. But here's the problem. The particles that scientists want to study often exist for less than 1/trillionth of a second before decaying into other particles. So you can't see them directly. You have to reconstruct them from the particles they decay into, the way an archaeologist reconstructs a dinosaur from scattered bones. This is where the anomalies started appearing. In 2021, an experiment called LHCb, which specializes in studying particles containing beauty quarks, also called bottom quarks, reported something strange. When certain B mesons decayed, they were producing muons and electrons at different rates than the standard model predicted. Now, according to the standard model, electrons and muons are essentially the same particle, just with different masses. They should be produced equally often in decays. This is called lepton universality, and it's been tested extensively. But the LHCb data showed muons being produced less often than electrons, by about 15%, with a statistical significance of 3.1 standard deviations. In particle physics, 3 standard deviations means there's about a 1 in 1,000 chance it's just a statistical fluctuation. That's not enough to claim a discovery, which requires 5 standard deviations, but it's enough to make physicists very, very interested. Dr. Sheldon Stone from Syracuse University, a member of the LHCb collaboration, said in 2022, "If this holds up, we're looking at a violation of lepton universality, which would require new physics beyond the standard model. Something is interacting differently with muons than with electrons, and we have no idea what." Then, in 2023, more data came in. The anomaly didn't go away. It got stronger. The statistical significance rose to 3.3 standard deviations, and other experiments started seeing similar things. The Bell 2 experiment in Japan found hints at the same lepton universality violation, independent confirmation from a different experimental setup. But it wasn't just B mesons. The Atlas and CMS detectors at CERN started seeing anomalies in completely different processes. High-energy collisions that produced certain combinations of leptons and quarks were coming out with slightly wrong probabilities. Not by much, just a few percent, but consistently across multiple channels. Dr. Fabiola Gianotti, Director General of CERN, addressed these anomalies in a 2024 conference. "We are seeing patterns in our data that suggest either extraordinary coincidences, systematic errors we haven't identified despite enormous effort, or genuine deviations from the standard model. The third option is simultaneously the most unlikely and the most exciting. And here's what keeps physicists up at night. These anomalies have a pattern. They're not random. They correlate with high-energy processes that probe the vacuum at extremely small distance scales. It's as if the harder you hit spacetime, the more likely you are to see it crack." Theorists immediately started proposing explanations. New force-carrying particles called Z-prime bosons. Exotic forms of matter called leptoquarks that can convert quarks into leptons and vice versa. Modifications to the Higgs mechanism itself. But there's another class of explanation that's more radical. What if the anomalies aren't due to new particles at all? What if they're due to the structure of spacetime itself? This is where quantum gravity enters the picture. We have a successful quantum theory of three forces: electromagnetism, the weak nuclear force, and the strong nuclear force. But gravity has resisted quantum treatment for nearly a century. Einstein's general relativity describes gravity beautifully, but it's not a quantum theory. And when you try to make it quantum, the mathematics breaks down. You get infinities that can't be removed. String theory is one attempt to solve this. It proposes that fundamental particles aren't points, but tiny vibrating strings, and the different vibrational modes correspond to different particles. In string theory, gravity emerges naturally, and the theory is mathematically consistent. But string theory requires extra spatial dimensions, typically 6 of them, curled up so small we can't detect them. If those extra dimensions exist, particles moving through our three-dimensional space are actually moving through a higher dimensional space, and their behavior depends on the geometry of those hidden dimensions. A wrinkle or defect in the extra dimensions could cause particles to behave abnormally. Loop quantum gravity takes a different approach. It proposes that spacetime itself is quantized, made of discrete loops of space at the Planck scale. If spacetime is fundamentally grainy rather than smooth, particles at high enough energies would start to notice the graininess. They'd scatter off the quantum structure of space itself. The CERN anomalies could be the first evidence that spacetime is quantized. The particles aren't behaving strangely because of new forces or particles. They're behaving strangely because at high enough energies, they're bumping into the pixelated nature of reality itself. Think of it like this. Imagine you're watching a movie on a huge screen. From far away, the image looks smooth and continuous. But if you walk right up to the screen, you start to see individual pixels. The image breaks down into discrete dots of color. Now imagine you're a particle traveling at near light speed, and you're smashing into spacetime with extraordinary energy. You'd start to see the pixels of space itself. And if spacetime is quantized, that has profound implications. It means space and time might not be fundamental at all. They might be emergent properties of something deeper, the way temperature is an emergent property of molecular motion. At the deepest level, there might be no space and no time, just a network of quantum information. And what we experience as spacetime is a kind of collective illusion arising from that network. Dr. Carlo Rovelli, one of the founders of loop quantum gravity, put it beautifully. We are not in spacetime. We are spacetime. And spacetime is not a container, but a relationship between events, a way of organizing information. What CERN might be discovering is that this organization has seams, places where the information structure is defective. This is where things get truly strange, because if spacetime is information, then the cracks CERN is detecting might be information corruption, errors in the cosmic code. And the question becomes, what's causing the corruption? Is it just random quantum noise? Or is something interfering with reality's source code? I know that sounds like science fiction, but we're past the point where our intuitions about reality are useful. Every experiment we do at these energies takes us further from the world of human experience and deeper into a realm where only mathematics can guide us. And the mathematics is suggesting something extraordinary. Let me show you where this leads. Now we need to talk about the vacuum, because understanding what vacuum means in physics is absolutely crucial to grasping the significance of CERN's discovery. In everyday language, a vacuum means empty space, the absence of matter and air. In physics, vacuum means the lowest energy state of a quantum field. And here's the first twist. Even at its lowest energy state, a quantum field isn't truly empty. It's seething with activity. The reason comes from Heisenberg's uncertainty principle, which states that you can't simultaneously know both the position and momentum of a particle with perfect precision. There's a fundamental limit to how much information reality contains. But the uncertainty principle also applies to energy and time. You can't know both the energy of a system and the exact time with perfect precision. This means that over short enough timescales, energy can fluctuate wildly without violating any conservation laws. Particles can pop into existence from nothing, as long as they disappear quickly enough that nobody can catch them violating energy conservation. These are called virtual particles, and they're not just theoretical. They have measurable effects. One of the most famous is the Lamb shift, discovered in 1947. The energy levels of electrons and hydrogen atoms are shifted slightly from what Dirac's equation predicts, because the electrons are constantly interacting with virtual photons emerging from the quantum vacuum. This shift has been measured to extraordinary precision, and it matches quantum field theory perfectly. So the vacuum isn't empty. It's a quantum field in its ground state, but that ground state is full of fleeting particles and antiparticles, appearing and disappearing billions of times per second in every cubic centimeter of space. Now here's where it gets weird. In quantum field theory, fields have potential energy, like a ball on a hill. The ball wants to roll to the bottom of the hill, to the lowest energy state. For most fields, we know where the bottom is. The electromagnetic field's lowest energy state is zero field, no photons. The electron field's lowest energy state is also zero, no electrons. But for some fields, the shape of the potential energy curve is more complicated. There might be multiple valleys, multiple local minima. The field might be sitting in a valley that feels stable, but there's an even deeper valley somewhere else. The Higgs field is exactly like this. The Higgs field gives mass to particles, and its potential energy curve has a famous Mexican hat shape. At high energies, like immediately after the Big Bang, the Higgs field was at the peak of the hat at zero field value. But as the universe cooled, the Higgs field rolled down into the brim of the hat, settling at a non-zero value. This is called spontaneous symmetry breaking, and it's the reason particles have mass. But here's the terrifying question. Is the brim of the Mexican hat where the Higgs field is sitting right now the lowest possible energy state? Or is there a lower valley somewhere else? A state where the Higgs field has a different value, and the laws of physics are completely different? Based on the measured mass of the Higgs boson, discovered at CERN in 2012, and the measured mass of the top quark, physicists can calculate the shape of the Higgs potential at higher energies. And what they found is disturbing. At very high energies, around 10 to the 11 GeV, the Higgs potential might turn negative. If it does, that means our current vacuum state isn't the lowest energy state. There's a lower state, a true vacuum, and we're sitting in a false vacuum. Dr. Joseph Liken and Dr. Stephen Hawking co-authored a paper in 2014 explicitly discussing this. They calculated that our vacuum is metastable, meaning it's stable for now, but could decay. Hawking's last paper, published after his death in 2018, dealt directly with vacuum instability and the implications for the universe's fate. The lifetime of a false vacuum depends on quantum tunneling. Even though there's an energy barrier between the false vacuum and the true vacuum, quantum mechanics allows the field to tunnel through the barrier, the way a particle can quantum tunnel through a wall, even though it doesn't have enough energy to go over it. The probability of this tunneling is extraordinarily low. Based on current calculations, the average time for vacuum decay to occur in any given region of space is far, far longer than the current age of the universe. We're talking 10 to the 100 years or more. So there's no immediate danger. And this is a huge, but those calculations assume the vacuum is perfectly homogeneous. If there are defects in spacetime, regions where the Higgs field is already fluctuating abnormally, those defects could act as nucleation sites for vacuum decay. They dramatically lower the barrier, making tunneling far more likely. Think of it like this. If you have a supersaturated solution, it can stay liquid even though it wants to crystallize, as long as there are no impurities or surfaces for crystals to start growing on. But drop in a single grain of sand, a single nucleation site, and the entire solution crystallizes instantly in a cascade. What if space-time has defects, quantum scale impurities, and CERN is detecting particles interacting with those defects? What if the cracks they're seeing are nucleation sites? This is why some physicists took the LHC's construction seriously as a potential risk. Not because they thought it was likely to destroy the world, but because high-energy collisions could theoretically nucleate vacuum decay if our vacuum is false, and if space-time has defects. The risk was analyzed extensively before CERN was turned on. The conclusion was that cosmic rays hit Earth's atmosphere with far more energy than the LHC produces, and they have been doing so for billions of years without triggering vacuum decay. If it could happen, it would have happened already. But that analysis assumed cosmic rays interact with atmospheric nuclei, which are relatively diffuse targets. The LHC slams protons into other protons, concentrated targets, which creates much higher energy densities, even if the total energy is lower. It's the difference between spreading a hammer blow over a large board versus concentrating it on a single nail. No physicist seriously thinks the LHC will destroy the world. But the fact that the question was even asked and analyzed tells you how strange the physics is at these energies. And now CERN is detecting anomalies that suggest spacetime might already have defects. The false vacuum might already be under stress. The universe might already be cracking. Let me be clear about what would happen if vacuum decay started. A bubble of true vacuum would form, maybe at a point in space, maybe in one of CERN's collisions, maybe somewhere random in the cosmos. The bubble wall would expand outward at the speed of light. Outside the bubble, physics as we know it. Inside the bubble, completely different physics. You wouldn't see it coming. Light from the bubble wall travels at the same speed as the bubble wall itself. There would be no warning. One instant you exist, and the next instant, before any signal can reach your neurons, the wall passes through you and you cease to exist in any meaningful sense. The atoms in your body would rearrange according to new physical laws. Maybe quarks can't form bound states in the true vacuum, so protons don't exist. Maybe the electromagnetic force is weaker, so atoms can't form. Maybe the true vacuum is so low in energy that no complex structures can exist at all. We wouldn't die. We'd simply be erased and replaced with something that bears no relationship to what we were. But here's the strange comfort. If vacuum decay is happening, there's literally nothing we can do about it. We can't see it coming, can't stop it, can't escape it. It's the ultimate cosmic risk. So in a weird way, there's no point worrying. Either it happens or it doesn't, and you'll never know if it does. The real question is, are the CERN anomalies actually signs of incipient vacuum decay? Or are they something else entirely? Something potentially even stranger? What if the cracks in spacetime aren't leading to vacuum decay, but to something leaking in from outside our reality? Stay with me. This is where we need to talk about the multiverse, not as speculation, but as serious physics. And I promise you, the implications are more bizarre than any science fiction. The multiverse isn't a fringe idea anymore. It's a natural consequence of several of our best theories. Let me show you why physicists take it seriously. First, there's cosmic inflation. In the 1980s, Alan Guth and others proposed that the universe underwent a period of exponentially rapid expansion in the first fraction of a second after the Big Bang. This inflation explains several puzzles, like why the universe is so uniform in all directions and why space is geometrically flat. But inflation, once it starts, is hard to stop. The quantum field driving inflation, called the inflaton field, doesn't decay everywhere at once. It decays in patches, creating bubble universes. Each bubble is a separate universe with its own laws of physics. depending on how the inflattened field decayed and what vacuum state it settled into. Our universe is one bubble, but inflation predicts there are infinitely many other bubbles, an eternal process creating new universes forever. This is called eternal inflation, and it's a natural consequence of the mathematics. Most cosmologists accept that inflation happened because it explains the data so well. And if inflation happened, eternal inflation and the multiverse are almost unavoidable. Second, there's string theory. String theory requires 6 extra spatial dimensions beyond our familiar 3. These extra dimensions are compactified, curled up into complex geometric shapes called Calabi-Yau manifolds. The exact shape determines the physics of our universe, things like particle masses and force strengths. But there are an enormous number of possible Calabi-Yau shapes, estimated at around 10 to the 500. Each shape gives a different universe with different physics. This is called the string theory landscape. We live in one valley of this landscape, one configuration of the extra dimensions. But there are countless others. Third, there's quantum mechanics itself. The many worlds interpretation, proposed by Hugh Everett in 1957, suggests that every quantum measurement causes the universe to split into branches, one for each possible outcome. You don't collapse the wave function when you measure. Instead, you become entangled with the measurement apparatus, and the universe branches, so that every outcome occurs in some branch. In this view, there's no randomness in quantum mechanics. Everything that can happen does happen, somewhere in the branching structure of reality. There are versions of you who made every possible choice at every decision point in your life. The reason quantum mechanics looks probabilistic to us is that our consciousness is confined to one branch, and we can't see the others. This sounds crazy, but it's mathematically the simplest interpretation of quantum mechanics. It doesn't require wave function collapse, which no one understands anyway. It just takes the Schrödinger equation seriously and applies it to everything, including observers. So we have 3 independent lines of reasoning, all suggesting that our universe is just one among many, maybe infinitely many. Now here's where CERN's discovery becomes truly mind-bending. What if the cracks in spacetime aren't cracks at all? What if they're interfaces? Boundaries where our universe touches another universe? In eternal inflation, bubble universes can collide. When 2 bubbles expanding through the inflating space happen to touch, they interact along a boundary surface. If we're in one bubble and another bubble collided with us billions of years ago, that collision would leave a mark in the cosmic microwave background, a circular pattern of slightly different temperatures. Physicists have looked for these collision signatures, and there are a few tentative hints in the data, but nothing conclusive. But what if the collision wasn't billions of years ago? What if it's ongoing? What if our universe is currently rubbing up against another universe, and the places where they touch are microscopic, quantum-scale boundaries that particles occasionally interact with? That would look exactly like what CERN is seeing, occasional anomalies where particles behave as if they're interacting with something that shouldn't be there. Dr. Raymond Sundram at the University of Maryland has worked extensively on brain cosmology, the idea that our universe is a 3-dimensional membrane embedded in a higher dimensional space. In his models, particles are confined to the brain, but gravity can leak into the extra dimensions. This explains why gravity is so much weaker than the other forces. If there are other brains, other universes, nearby in the extra dimensions, then even though we can't see them directly, high-energy particles might occasionally quantum tunnel from our brain to another brain and back. The probability would be tiny, but CERN is running trillions of collisions. Tiny probabilities become detectable. Those particles would appear in our detectors with properties that don't quite match our physics, because they've briefly interacted with a region of spacetime where the laws are different. They'd look like anomalies. Think about that. The weirdness CERN is detecting might be particles that have briefly visited another universe. Or here's an even stranger possibility. What if consciousness itself is leaking between universes? In the many worlds interpretation, every decision you make creates branches. But your conscious experience is singular. You only perceive one branch. Why? What determines which branch you experience? Some physicists, notably David Deutsch at Oxford, suggest that consciousness is the mechanism that selects branches. Your subjective experience is determined by which branch your consciousness inhabits. But consciousness isn't localized to a single point in spacetime. It's distributed, quantum entangled with the particles in your brain. If your consciousness is quantum entangled, it exists in a superposition across many branches until something fixes it to one branch. That fixing might not be perfect. There might be quantum leakage, moments where your consciousness briefly touches branches it's not supposed to be in. This would explain some deeply weird phenomena. Déjà vu, the sense that you've experienced something before, even though you know you haven't. Mandela effects, where large groups of people remember historical events differently than records show. Glitches in perception, where reality seems temporarily wrong. What if these aren't just psychological quirks? What if they're real? Brief moments where your consciousness is experiencing multiple branches simultaneously, or where quantum tunneling has allowed information from other branches to leak into your current branch. And what if the stress on the vacuum, the cracks in spacetime that CERN is detecting, are making this leakage more common? What if, as reality becomes unstable, the boundaries between branches become more porous? I know this sounds like I've gone off the deep end, but I'm not making this up. These are serious proposals from serious physicists published in peer-reviewed journals. The universe is far, far stranger than we evolved to comprehend. Let me ground this again with hard data. In 2024, a team led by Dr. Patricia Burchat at Stanford analyzed cosmic ray data from the Pier Auger Observatory in Argentina. They found statistically significant anomalies in ultra-high energy cosmic rays, particles with energies above 10 to the 20 electron volts, energies that shouldn't even be possible. The most energetic cosmic rays ever detected, called oh my god particles, carry as much energy as a baseball thrown by a major league pitcher, concentrated in a single proton. We don't know what cosmic events can produce such particles. Supernovas aren't powerful enough. Active galactic nuclei might be, but the particles would lose energy traveling intergalactic distances, and yet they arrive with absurd energies. Dr. Burchat's team found that these ultra-high energy cosmic rays don't decay the way they should. They travel farther than predicted before interacting. It's as if they're not fully interacting with our spacetime, as if they're partially ghosting through our universe, spending some of their time in another dimension or another brain. And the anomalies correlate with the anomalies CERN is seeing. Not perfectly, but statistically. As if the same underlying phenomenon, whatever is causing space-time defects, is affecting both lab experiments and cosmic rays. This is where the story gets a time dimension. Are the cracks spreading? Are they getting worse? Or have they always been there and we're only now detecting them because our instruments are finally sensitive enough? We don't know. But there's some evidence, tentative and controversial, that anomalies are becoming more common. A 2025 analysis of archival data from older particle accelerators, experiments from the 1990s and 2000s, shows hints of similar anomalies, but much weaker. As if space-time was less damaged back then? If that's real, and it's a big if, because systematic errors in comparing different experiments are huge, it suggests the cracks are growing. Reality is becoming less stable over time. Why would that be? One possibility is vacuum decay. If a bubble of true vacuum nucleated somewhere in the distant universe billions of years ago, and it's been expanding toward us at light speed, we wouldn't see it coming. But we might detect precursor effects, quantum correlations spreading ahead of the bubble, destabilizing the false vacuum even before the bubble wall arrives. Another possibility is dark energy. The accelerating expansion of the universe is driven by something with negative pressure, something that pushes space apart. We call it dark energy, but we have no idea what it actually is. One possibility is that it's vacuum energy, and if vacuum energy is increasing over time, it's adding stress to spacetime. Eventually, spacetime might not be able to hold together under that stress. Or maybe the cause is external. Maybe a collision with another universe is ongoing, and the collision is intensifying. Maybe we're sinking deeper into a brain collision, and as we do, the boundaries become more intrusive, more disruptive. Every possibility sounds like science fiction, but the data is real. The anomalies are real. Something is happening to the structure of reality, and it's showing up in our experiments. Before I take you deeper, I need you to engage. Comment below. Do you think consciousness could be leaking between universes? Have you experienced something that felt like a glitch in reality? And hit that subscribe button, because where we're going next, we're going to talk about what this means for you personally. How these cracks in spacetime could be affecting your daily life in ways you've never imagined. Let me shift gears and talk about something that's going to make this personal, because what's happening at the frontiers of physics isn't abstract. It has implications for your life, your consciousness, and your place in the cosmos. You've probably heard the phrase observer effect in quantum mechanics. The idea that observing a particle changes its state. But have you ever stopped to think about what that means for you as an observer? In quantum mechanics, measurement is physical interaction. When you observe a particle, you're interacting with it, usually with photons bouncing off it and into your eyes or instruments. That interaction disturbs the particle. So the observer effect could just be a technical issue about measurement. But there's a deeper problem. The math of quantum mechanics, the Schrödinger equation, describes particles as being in superposition, occupying multiple states simultaneously until they're measured. At that point, the wave function collapses to a single definite state. But the Schrödinger equation doesn't include wave function collapse. Collapse is added by hand as an extra postulate because that's what experiments show happens. But nobody knows why collapse occurs, or what counts as a measurement, or what makes an observer special. This is called the measurement problem, and it's been unsolved for nearly a century. Different interpretations of quantum mechanics give different answers. Copenhagen interpretation says collapse happens when a quantum system interacts with a classical measuring apparatus, but it doesn't define what makes something classical. Many worlds says collapse doesn't happen at all. Everything stays in superposition and the universe splits. Pilot wave theories say particles always have definite positions guided by a wave, and there's no collapse because there's no superposition in the first place. But there's another interpretation, rarely discussed outside philosophy of physics, called cubism or quantum Bayesianism. Proposed by Christopher Fuchs and Rudiger Schack, QBISM says that quantum states aren't descriptions of reality. They're descriptions of an agent's beliefs about reality. When you measure a particle and the wave function collapses, what's actually happening is that you're updating your knowledge. The particle was always in a definite state. You just didn't know what state until you measured. The wave function represents your uncertainty, not the particle's ontology. In cubism, quantum mechanics is fundamentally about information and experience. Reality is still objective, but quantum mechanics isn't describing reality directly. It's describing how conscious agents interact with reality and update their knowledge. This might sound like semantic games, but it has profound implications. If quantum mechanics is about experience, then consciousness is fundamental to the theory. You can't remove the observer from the picture. And if consciousness is fundamental, then the cracks in spacetime that CERN is detecting aren't just physical defects. They're defects in the information structure of reality, the structure that supports conscious experience. What if consciousness requires spacetime to have certain properties? What if your subjective experience, the fact that it feels like something to be you, requires spacetime to be continuous and stable? And what if the cracks are disrupting that continuity? There's some evidence, controversial and not widely accepted, That consciousness might be sensitive to quantum effects in the brain. Roger Penrose and Stuart Hameroff proposed that microtubules in neurons could support quantum coherence, and that consciousness arises from quantum computations in these microtubules, computations that collapse through a quantum gravity effect. Most neuroscientists are skeptical of this. The brain is warm and wet, conditions that destroy quantum coherence almost instantly. But Penrose and Hameroff argue that microtubules might protect quantum states long enough for them to matter. If they're right, then your consciousness is directly sensitive to the structure of spacetime at quantum scales. You're not just a passive observer of reality. You're an active participant, and your brain is quantum computing on the geometry of spacetime itself. And if spacetime has cracks, if reality is becoming unstable, your consciousness might be the first thing to notice. Have you ever experienced time distortion? Moments where seconds feel like minutes, or minutes feel like seconds? Standard neuroscience says this is just how the brain processes time, constructing a sense of duration from memory and attention. But what if it's more than that? What if your brain is detecting actual fluctuations in spacetime geometry? Einstein's relativity shows that time is not universal. Time runs at different rates depending on motion and gravity. Near a black hole, time slows dramatically compared to far away. But these effects are tiny in everyday life. GPS satellites experience it, but humans don't. Or do we? What if quantum fluctuations in spacetime cause tiny, localized time distortions? And what if your brain, because it's sensitive to quantum effects, can detect them? The distortions would be far too small to measure with clocks, but they might be large enough to affect the quantum processes that generate consciousness. This would explain a lot of anomalous experiences. The sense that time stopped during a car accident. The feeling of timelessness during meditation or flow states. Déjà vu, which might be your brain detecting a loop in space-time geometry, a region where the past and present are quantum entangled. I know this sounds speculative. It is speculative, but it's not unscientific. It's taking seriously the idea that consciousness is deeply integrated with the physical structure of reality, and that changes in that structure would have experiential correlates. And if the cracks in spacetime are growing, if reality is becoming less stable, then these anomalous experiences might be becoming more common. More people might be reporting glitches, synchronicities, moments where the world doesn't quite make sense. There's no scientific study of this yet. How would you even design one? But anecdotally, if you spend time in communities that discuss these experiences, there does seem to be an increase. More people talking about reality feeling different. More people experiencing what they describe as glitches. It could be social contagion, confirmation bias, the internet making rare experiences seem common. But it could also be real. Your consciousness might be the most sensitive instrument we have for detecting instabilities in spacetime. Let me take this further. What if the structure of spacetime affects not just your moment-to-moment experience, but the trajectory of your life? What if synchronicities, meaningful coincidences, are actual physical phenomena arising from quantum entanglement across time? Physicist John Wheeler proposed a concept called delayed choice. In quantum mechanics, you can set up an experiment where a particle's behavior in the past depends on a measurement you make in the future. The particle seems to retroactively change its history based on what you choose to observe. This has been demonstrated experimentally. In delayed choice quantum eraser experiments, the decision about what measurement to make is delayed until after the particle has already interacted with the apparatus. And yet, the particle's earlier behavior changes depending on the later decision. This suggests that quantum mechanics isn't just about uncertainty in the present. It's about the past and future being quantum entangled, interconnected in ways that don't respect the normal flow of time. Now extend this to your life. Every decision you make is at some level a quantum process. Neurons firing, ion channels opening and closing, chemical reactions in synapses. All of these are quantum events. If the future can affect the past in quantum mechanics, then your future decisions might be quantum entangled with past events. Synchronicities might be points where the entanglement becomes classically visible, where the correlation between past and future events is strong enough that you notice it. Carl Jung called synchronicity, and a causal connecting principle, a meaningful coincidence that couldn't be explained by cause and effect. But what if he was wrong about the acausal part? What if synchronicities are causal, but the causation runs backward in time through quantum entanglement? This would mean your life isn't just unfolding forward. It's also being pulled towards certain outcomes by future events reaching back through quantum connections. You're not just pushed by the past, you're pulled by the future. And if space-time has cracks, if the quantum structure is damaged, then these temporal connections might be disrupted. Your life path might become more chaotic, less coherent. Or conversely, the cracks might create new connections, new synchronicities, as different timelines or universes start to bleed into each other. People who work with quantum physics professionally often report experiencing more synchronicities. Pauli, one of the founders of quantum mechanics, was famous for the Pauli effect, or equipment would malfunction when he entered a room. Jung studied Pauli and developed his concept of synchronicity partly from their conversations. Is this just confirmation bias? Or do people who work closely with quantum systems become quantum entangled with them in ways that affect their everyday lives? I don't know. But I'm asking the question because if consciousness is fundamentally quantum, and if the quantum structure of reality is under stress, then your subjective experience is the front line of that stress. You might be feeling it without realizing what you're feeling. So here's what I want you to do. Pay attention. Over the next weeks and months, notice your experience. Notice moments where time feels weird. Notice synchronicities, coincidences that seem too perfect to be random. Notice dreams that feel prophetic or memories that don't quite fit. I'm not saying interpret these as supernatural. I'm saying treat them as data. If reality is cracking, your consciousness might be the sensor that detects it first, and document it. Share it, because if anomalous experiences are increasing, that's information. It might not be peer-reviewed science, but it's still a signal, and enough signals can point towards something real. Comment below if you've noticed anything strange recently. Any glitches, any experiences that made you question reality. I'm genuinely curious if there's a pattern. Now, let's talk about what this means for the big picture. Not just your life, but the fate of humanity and the cosmos. If space-time is cracking, we have to ask, is this fixable? Can we repair reality? Or are we just along for the ride as the universe unravels? The optimistic view is that the cracks are localized and stable. They're defects, but they're not spreading, and they don't threaten the overall structure. Space-time is robust enough to contain them, the way a crystal can have impurities without shattering. In this scenario, CERN's anomalies are fascinating new physics, maybe even gateways to understanding quantum gravity or accessing other dimensions, but they're not dangerous. We can study them, learn from them, maybe even use them. Some physicists have speculated that space-time defects could be engineered. If we understood how they form and what sustains them, we might be able to create them deliberately. And if they're boundaries to other regions of space-time or other brains, they could be traversable. They could be wormholes. A wormhole is a tunnel through space-time, connecting distant points. Einstein's equations allow them, but they require exotic matter with negative energy density, to hold them open. We've never found exotic matter, and most physicists think it doesn't exist. But space-time defects might be different. If there are cracks in the fabric, regions where the geometry is torn, they might not need exotic matter. The crack itself might be a pathway. If so, advanced civilizations might already be using them. This could explain some of the weirdness in UFO reports. Not saying aliens are visiting Earth, but if ultra-advanced beings exist somewhere in the universe or in other brains, and if they've mastered space-time engineering, They might travel through cracks in reality. From our perspective, they'd appear to violate physics. Instant acceleration, no visible propulsion, moving through solid objects. But from their perspective, they're not in our space-time fully. They're moving through the cracks, the regions where our laws don't fully apply. This is wild speculation, but it's speculation grounded in the actual physics of what CERN might be detecting. The pessimistic view is that the cracks are growing and we can't stop them. Space-time is under stress from vacuum instability, dark energy, or brain collisions, and the structure is going to fail. Not tomorrow, maybe not in our lifetimes, but on cosmic timescales soon. If vacuum decay occurs, it's instant and final, but there might be intermediate scenarios. Space-time might not collapse all at once. It might fragment, breaking into disconnected regions with different physics. Some regions might remain habitable, others might not. In this scenario, the far future universe is a patchwork, islands of stability surrounded by chaos. Civilizations would be trapped on their islands, unable to reach others because the space-time between them is broken. Or maybe the cracks don't destroy space-time, but change it. Maybe they're healing processes, the universe repairing itself by transitioning to a more stable configuration. What we experience as cracks might be the birth pangs of a new cosmic order. There's a concept in thermodynamics called annealing. If you heat a metal and cool it slowly, the atoms have time to rearrange into a low-energy crystalline structure. The metal becomes stronger. But if you cool it quickly, the atoms freeze in place in a disordered state, and the metal is brittle. The universe after the Big Bang cooled quickly. The Higgs field froze into its current value before it had time to find the true minimum. We might be living in a brittly frozen universe, and the cracks are the first signs that the universe is re-annealing, slowly rearranging itself into a more stable configuration. If that's true, the transition might not destroy everything. It might transform everything. The laws of physics would change, but gradually, with regions of old physics persisting as the new physics spreads. In this scenario, consciousness, because it's information rather than matter, might survive the transition. Your body would be destroyed and rebuilt according to new laws. But the information pattern that is you might persist, encoded in the structure of space-time itself. This is deeply speculative, bordering on metaphysics. But it's where the physics leads if you take seriously the idea that consciousness and information are fundamental. Dr. David Chalmers, a philosopher of mind, has argued that consciousness might be a fundamental property of the universe, like mass or charge. In his view, certain information processing systems have associated conscious experiences, and the laws of physics include psychophysical laws determining which physical states correspond to which experiences. If Chalmers is right, and if those psychophysical laws are encoded in the structure of spacetime, then changes to spacetime would change the laws of consciousness. The cracks might not kill consciousness. They might alter it, giving rise to new forms of experience we can't currently imagine. Post-transition, if there is a transition, the universe might be populated by conscious entities with completely different subjective experiences. They might perceive dimensions we can't see, experience time non-linearly, or exist in superposition across multiple locations simultaneously. And here's the truly mind-bending possibility. We might already be interacting with them. If the cracks are boundaries between different physics, and if consciousness can exist in both, then beings adapted to the cracked regions might be trying to communicate with us. We wouldn't recognize the communication as such because our consciousness is tuned to our physics. But we might perceive it as anomalies, glitches, voices in the noise, patterns in randomness. This could explain some of the stranger aspects of human experience: religious visions, mystical experiences, reports of entities or presences that seem real but don't fit into our physical understanding. I'm not saying these are literally communications from beyond. I'm saying that if space-time is cracking, if reality has boundaries and interfaces, then consciousness existing near those boundaries might experience things that consciousness in stable regions doesn't. Shamanic traditions often speak of traveling between worlds, accessing realities behind or beyond the ordinary world. What if that's not metaphor? What if certain practices, meditation, entheogens, extreme states, allow consciousness to approach the cracks in spacetime and perceive what's on the other side? Modern neuroscience would say these are hallucinations, the brain generating experiences without external stimuli. But what's the difference between a hallucination and a genuine perception of something that exists in a different region of spacetime? How would you tell? You couldn't, unless the perception gives you information you couldn't have obtained otherwise. And there are documented cases of this. Remote viewing experiments at Stanford Research Institute in the 1970s and 80s showed statistically significant results. People could describe distant locations they'd never seen with better than chance accuracy. The CIA took it seriously enough to fund the program for 20 years. When it was declassified, the official conclusion was that the results were intriguing but not reliable enough for intelligence work. But intriguing means something was happening. What if remote viewing works by consciousness briefly accessing the cracks, regions where space-time geometry allows information from distant locations to leak through? It wouldn't work reliably because the cracks are rare and unstable. But occasionally, under the right conditions, information would transfer. This is the edge of known physics. We're in territory where science blends into philosophy, and philosophy blends into experience. But that's appropriate, because the cracks in reality blur those boundaries. Everything I'm describing, the anomalies at CERN, the quantum nature of consciousness, the possibility of space-time defects connecting to other realities, all of it points to a single profound conclusion. Reality is not what you think it is. You are not what you think you are. And the boundaries you take for granted, between mind and matter, between self and world, between past and future, might be artifacts of living in a temporarily stable region of a far vaster and stranger cosmos. The cracks aren't just in space-time. They're in the illusion of separation. And as they grow, we might discover that we've never been separate at all. Take a moment, let that sink in. Then hit that like button and subscribe, because we're not done. There's more, and it gets even stranger. I want to bring this back to something concrete, something you can relate to your own life, because the danger with this topic is it becomes so abstract that it loses meaning. But what's happening at CERN, the cracks in reality, have immediate and practical implications for how you should think about your existence. Let me start with mortality. You're going to die. That's a fact. Your body will stop functioning, your brain activity will cease, and the person you are will end. This is terrifying for most people, which is why every human culture has developed beliefs about what happens after death. Afterlives, reincarnation, spiritual realms. Modern materialist science says these are comforting fictions. When your brain stops, you stop. There's no you to continue because you are your brain. And when the brain dies, you're gone. But quantum mechanics complicates this picture enormously. If consciousness is a quantum phenomenon, if your subjective experience arises from quantum coherence in your neurons, then your consciousness isn't localized to a single moment in time. It's spread out, entangled with its own past and future. In the many worlds interpretation, when you die in this branch, you continue existing in other branches where you didn't die. Every moment you're alive, there are branches where you die randomly. A brain aneurysm, a car accident, whatever. But there are also branches where you survive, and your consciousness continues in those branches. You can't experience the branches where you die, because in those branches, you don't experience anything. So from your subjective perspective, you only ever experience the branches where you survive. This is called quantum immortality, and it's a natural consequence of many worlds if consciousness is quantum. It doesn't mean you survive forever. Eventually, you'll age to the point where there are no branches where your body functions anymore. But it means your subjective experience never includes your own death. From your perspective, you always survive improbably, right up until the moment where survival is physically impossible. Now, how does this relate to spacetime cracks? If spacetime is unstable, if there are boundaries between different physics, then the branches of the wave function aren't just in our universe. They extend across all possible configurations of spacetime, all possible universes in the multiverse. When you die here, your consciousness might not end. It might transfer to a version of you in another universe where you didn't die. Not metaphorically, literally. The information pattern that is you might be conserved across the multiverse, and death in one universe is just a transition to another. This sounds like wishful thinking, and maybe it is, but it's not inconsistent with physics. If consciousness is information, and if information is conserved in quantum mechanics, which it is, then the information pattern that constitutes your consciousness can't be destroyed. It can only be transformed or transferred. The cracks in spacetime might be the mechanism for that transfer. When your brain dies, the quantum coherence that supports your consciousness collapses. But if spacetime has defects, the information might not dissipate into thermal noise. It might leak through the cracks into another region of spacetime, another universe, where it recoheres in a different physical substrate. You wake up disoriented in a body that's almost but not quite like your old body, in a universe that's almost but not quite like your old universe. The differences are subtle. Most people wouldn't notice. But occasionally, you might remember something that doesn't quite fit, a memory from a different branch. This would explain the Mandela effect more deeply. It's not that groups of people remember wrong. It's that they remember correctly, but from a different branch, and somehow their memories leaked across. I know this sounds insane, but I want you to consider it seriously. Not because I'm asking you to believe it, but because I want you to understand that the physics we're discovering is so strange that ideas like this are no longer obviously wrong. They're possibilities. And if they're possibilities, then the way you relate to death, to loss, to the fear of ending might change. Not because you're adopting a comforting belief without evidence, but because the evidence, the actual data from particle physics and quantum mechanics, suggests that the universe is far more hospitable to consciousness than you might think. Let me give you another practical implication. Decision-making. Every day, you make choices. Small ones, like what to eat for breakfast, and large ones, like what career to pursue or who to marry. You probably think about these choices as selecting one path from several possible futures. But if the many worlds interpretation is correct, you're not selecting one path. You're determining which branch you consciously experience, while all other branches also occur with other versions of you. This reframes decision-making completely. The question isn't, which future should I create? Because all futures are being created. The question is, which version of me do I want to be? Or, which branch do I want to ride? And here's where it gets wild. If consciousness can leak between branches through space-time cracks, then the version of you in this branch might be influenced by decisions made by versions of you in other branches. Your intuitions, your gut feelings, might be information transfer from branches where you made different choices and experienced the outcomes. When you have a strong intuition that you should do something, even though you can't rationally justify it, that might be your parallel selves in other branches, sending information back through quantum entanglement. This sounds like pseudoscience, but it's based on taking quantum mechanics seriously. If the wave function is real, if all branches exist, and if consciousness is quantum, then information transfer between branches isn't impossible. It's just unlikely in normal spacetime. But in cracked spacetime, it might be common. So my advice, weird as it sounds, trust your intuitions more. Not blindly. You still need to think rationally. But when you have a strong feeling that doesn't come from any obvious source, consider that it might be signal, not noise. It might be information from another version of you who's already walked that path. Here's another practical implication. Connection. You've probably felt, at some point in your life, a deep sense of connection to another person. Not romantic necessarily, though it can be. Just a sense that you understand them at a level beyond words, that you're connected in some fundamental way. Conventional psychology says this is empathy, the ability to model another person's mental states in your own brain. But what if it's more than that? What if at the quantum level, human brains can become entangled? Quantum entanglement creates correlations between particles that can't be explained by any local theory. Einstein called it spooky action at a distance. If you measure one entangled particle, the other particle's state changes instantly, no matter how far apart they are. This has been proven experimentally thousands of times. It's real. And if quantum processes in the brain support consciousness, then two people whose brains have interacted extensively, through conversation, shared experiences, physical proximity, might develop quantum entanglement between their neurons. If they do, then their conscious experiences would be correlated. They'd intuitively sense each other's emotional states. They'd think of each other at the same time. They'd have shared dreams or synchronous experiences. And if space-time has cracks, if the barriers between different regions of reality are weakening, then quantum entanglement between brains might become stronger and more common. You might find yourself feeling connected to people you've never met, or feeling disconnected from people you used to be close to as the quantum correlations shift. This is testable, in principle. You'd need to measure quantum coherence in neurons from different people, can look for correlations. Nobody has done this yet because the technology is barely at the point where it's possible. But in the next decade or two, you might have data on whether human brains can be quantum entangled. If they can, that fundamentally changes what it means to be an individual. You're not an isolated consciousness trapped in a skull. You're a node in a network of entangled consciousnesses, affecting and being affected by others at the quantum level. Your thoughts might not be entirely your own. Some of them might be reflections of quantum correlations with other minds. And the boundary between self and other, which seems so clear, might be a useful fiction, an approximation that breaks down when you look closely enough. The cracks in space-time, by making quantum effects more prominent, might be revealing this truth. We're all connected, not metaphorically, but physically, through the quantum structure of reality. And if that's true, then your actions affect not just you, not just the people immediately around you, but the entire network. Every decision you make sends ripples through the quantum entanglement connecting all consciousness. This is why ethics matters on a cosmic scale. You're not just responsible for your local effects. You're responsible for the pattern you contribute to the collective. And in a cracked reality, where quantum effects are amplified, your contribution matters more than ever. I want to pause here and ask you to reflect. Have you felt more connected recently, or more isolated? Have your relationships felt deeper or stranger? Have you noticed synchronicities with people, moments where you and someone else think or feel the same thing simultaneously? If so, you might be experiencing the effects of a quantum entangled reality where the boundaries are weakening. Comment below with your experiences. And if this is resonating with you, share this video. Because if what I'm describing is real, then getting this information to more people might strengthen the collective network. We might be able to navigate the cracks together in ways we can't alone. Now, let's bring this to a conclusion. We've covered a lot, from particle physics at CERN, to the nature of consciousness, to the structure of spacetime itself. Let me tie it together and leave you with a message that I hope is empowering rather than frightening. Here's the core truth. Reality is not solid. It never was. What you experience as the stable, predictable world is a temporary configuration of quantum fields in a metastable vacuum state, held together by forces and symmetries that could change at any moment. The cracks CERN is detecting are signs that this configuration is under stress. Maybe the stress is natural, just the universe aging and settling. Maybe it's from external forces, collisions with other universes, or transitions in the vacuum state. We don't know yet. But what we do know is that you, your consciousness, your experience of being a self, is not separate from this process. You're not a passive observer watching reality from outside. You're part of the structure. Your consciousness is woven into the quantum fabric of spacetime. And that means you have a role to play. I don't mean that in a grandiose, you can save the universe sense. I mean it practically. The choices you make, the attention you pay, the connections you form, all of these contribute to the pattern of reality. In a stable universe, individual contributions are negligible. But in a cracking universe, where the structure is under stress and quantum effects are amplified, individual contributions matter more. Small perturbations can cascade into large effects. You might feel insignificant. One person among 8 billion on a small planet in a vast cosmos. But if consciousness is quantum, and if quantum effects are non-local, then your consciousness is entangled with the consciousness of others, and the pattern you create extends beyond your immediate physical location. You're not just a local phenomenon. You're a node in a cosmic network, and the quality of your node, the clarity and coherence of your consciousness, affects the whole network. So here's what I want to leave you with. Pay attention. Be present. Cultivate awareness. Not because it will save you from vacuum decay, it won't, but because in an uncertain reality, consciousness is the one thing you can refine and strengthen. Form connections. Engage deeply with others. Build relationships that are genuine and meaningful. These relationships create quantum entanglements, and those entanglements are stabilizing. They're threads that hold the pattern together. Trust your intuition. The cracks in spacetime might be making the boundaries between past, present, and future more porous. Information might be flowing in ways that seem impossible. Your gut feelings might be more accurate than your rational analysis, because they're integrating information from sources you're not consciously aware of. And finally, don't be afraid. Yes, reality is uncertain. Yes, the universe might be unstable. Yes, we're living in a time when fundamental truths are being questioned and revised. But you've always been living in that universe. You just didn't know it. The only thing that's changed is your awareness. And awareness is power. The cracks in reality are not endings. They're openings. Opportunities to see beyond the illusion of solidity, to understand that the universe is far more fluid and interactive than you were taught. You're not a fixed entity waiting for an inevitable death in a dying universe. You're a dynamic pattern of information and consciousness, entangled with all other patterns, co-creating reality moment by moment. The cracks reveal this truth. They show you that reality is not given. It's made, and you're one of the makers. So as CERN continues to probe the boundaries of spacetime, as physicists unravel the mysteries of quantum gravity and vacuum stability, remember that you're part of the experiment. Your consciousness is the instrument measuring reality, and what you find depends on how you look. Reality is cracking, but maybe it's cracking open, revealing something deeper, more beautiful, and more interconnected than the surface ever suggested. The journey through the cracks is just beginning, and you're not just observing it, you're living it. You're it. Thank you for staying with me through this exploration. If this changed how you see reality, hit that subscribe button and share this video with someone who needs their mind blown. Drop a comment telling me what you're taking away from this, what questions you still have, and how you're going to approach your life differently now that you know the universe might be cracking. Remember, we're all in this together, connected through quantum entanglement in shared consciousness, navigating an uncertain reality with nothing but awareness and each other. And maybe, just maybe, that's enough. The cracks are growing, but so are we. And in the space between the cracks and the boundaries and interfaces where different realities touch, that's where the future is being born. Be part of that birth. Stay curious, stay connected, Stay conscious, and I'll see you in the next video, where we'll explore even deeper into the quantum mysteries that are reshaping our understanding of everything. Until then, keep questioning reality. Because reality, as CERN has shown us, is stranger than anyone ever imagined.